Claudio Jeker is going to talk about the OpenBSD network stack. Those of you who work with BSD know that the network stack is one of the crown jewels of the system. Since the early BSD days, the different projects have gone different directions with the code. So now we're going to see what OpenBSD has done recently.
Yeah. So I will talk about the OpenBSD network stack, and when I did these slides, I realized afterwards that if I added 2 slides more to this presentation, it would be actually a movie. So I will have to I have to talk quickly and try to skip some slides perhaps, because it may take time. Already told, it's mostly based on the old BSD 4.4-based code, and the best reference for this is still the TCP/IP illustrated volume by Stevens. And everybody that wants to hack on network stacking code should actually have this code handy as reference, because it's very good to have the book around, especially if you don't understand the code. Everything IPv6-based is coming from Kami. So there are also some good books about how stuff is working in IPv6 that people should probably have around. Stuff made, OpenBSD made a lot of stuff, or enhancements of the network stack that other BSDs were also trying to get. So we have, we developed PF, which is probably the ultimate stateful packet filtering engine. Then we integrated AltQ together with PF to do traffic shaping and QoS. And in the end, the last additions were the routing daemons that we wrote, like BGP, OSPFD, and then later on RIPD, and now the IPv6 version of OSPF, OSPF 60. The network stack is more or less looking like this in a very simple way. We have the lowest layer, we have the drivers, and I will not cover the drivers. They're in their own land, and they're totally different compared to the rest of the kernel. Then on the other side, on the opposite side of the network stack, there is the socket API, which is used to talk to the user land, to the applications, to attach and everything. In between N is the big box, that's the network stack itself, which a large part of the code, and actually the code where a lot of magic happens, is the routing table code. And then the last bit, and a very important bit, is the mbuf, which is the memory management for the network stack. So we have these 4 main blocks, we have the socket API, we have the network stack, we have the mbuf API, because, yeah, we'll see that later, and we have the routing table. So the second API is used to do network connections, opening network connections from user land. It's a standard API across even multiple operating systems, so it's probably the most successful story of BSD, because even Windows has the socket API or accepted it. So we are really try to avoid changing massively things in the socket API. So we try to not touch it too much. And especially I don't like to touch it because my main interest is routing, so I don't have to play around with user land interaction at all. mbufs. mbufs are here to allocate memory for packets. So most of the time they're used for that, but even some other data is stored into mbufs. They can be changed, and they can be extended with external buffers to have larger size. An mbuf is by default 256 bytes big, and a normal Ethernet packet with 1.5Ks would just need too many of these mbufs to actually build up a huge chain. So an external buffer is by default used in a cluster, which is 2K big. So a packet just fits nicely into that. The mbufs are now backed by our pool memory management system, which gives us a lot more mbufs than a couple of years ago. So many memory restrictions we had are now gone. The biggest problem of mbufs is that they're actually not a real API. They're just a collection of functions to fiddle around with mbufs and their pointers, and most of them have at least evil side effects. Some have really evil side effects, and they're the #1 reason for network-related bugs. So every time your network, most of the time your network stack is crashing, it's mbuf handling. The other one is probably the routing table. So these are the two biggest problems we have. And the mbuf API is also responsible for the lost bump in our magic number on the home page that we had to do in the last 10 years. So this is really a big issue that we currently have with this API. This picture shows the way that mbufs can look like. So we have a simple mbuf with just a little bit of data. We have an mbuf with a packet header in it. So every packet starts with mbuf with a packet header. And additional data is stored in this packet header that is necessary to identify stuff in the packet. Like the receiving interface is stored inside the packet header. Then we have an mbuf with an external cluster, and this one here has annexed structures inside the mbuf to handle all the necessary information that is needed to know how to handle this external buffer that is attached there. Then there's two ways of chaining mbufs. So you can chain mbufs on a per packet level. So you have an mbuf, and here is an mbuf with a cluster together, and you connect them through the mnext pointer. So that's building up a chain, a large packet in the end. And then there is another way you can chain mbufs together, through the mnext packet pointer. So the mnext packet pointer is used to connect multiple packets together. So these are two different packets, and this is mostly used like in the UDP receive buffer, where you actually want to have you want to be able to distinguish between packets you receive, so that when you do a receive call, that you just get one packet, and then the next one is moved up to the top of the receive buffer, and you can just like DQ them one by one. So they're just chained together in this buffer. We added them later on the so-called mbuf tags, which is a way to attach metadata to a packet. So this is mostly used to prevent loops inside the network stacks that we have when we use tunnel interfaces like GIF, GRE, or IPsec, where we have the packet coming in, it's modified, and then re-enters the same function again, like most of the time IP output. We have to ensure that we don't create a loop and just like end up in a do loop inside the kernel. Then you have to reboot it like I had to do. The structure of an mbuf tag is a simple timeline value kind of structure, it's data structure. you can actually store almost anything in that. And most of them are very simple. There are some problems with the mbuf tags. So because they're time length value, we have to use the kernel malloc version of the memory allocator. The malloc is pretty slow. And at the same time, we're just building up a linear list of mbuf tags. So searching mbuf tags, especially as many are used, is getting a problem. So this is more of the way they look like. You have the mbuf, and then you have the mtags connecting to the mpacket header. They're stored inside the head node is stored inside the mpacket header because they're only per packet per mbuf fragment. Now, as I said, there are some performance problems, and PF was actually the most massive user of these mbuf tags. Every packet got one of these tags connected to it. And so as soon as you enable PF, a lot of mbuf tags are all constantly allocated and freed. And we figured out that moving this metadata from an mbuf tag directly into the packet header would gain us performance. And when we did this change, we actually doubled the performance of PF on slow box like a Socrates. And that's pretty amazing by just like changing something very little. Now to the network stack. The network stack is this is more or less just an overview. It's a 4-layer system, so there's a link layer, network layer, a transport layer, an application layer. Most code of the network stack is just here to verify packets and figuring out where to put them later on. There is a lot of if cases to figure out if the edge cases are correctly, and there are quite a few protocols implemented in the network stack. So this is more or less a big overview of how packets flow through the network stack, and I will now zoom in on parts of it and go through the network stack. So this is the first thing. When a packet comes in from the wire, it normally produces a driver receive interrupt. And then the driver will dequeue the packet from the DMA ring and move it on, further on, to the layer 2 functions, which are, in most cases, ether input. And ether input will strip off the header of the link layer 2, so the Ethernet header, and start to process the packet. So if it is a VLAN packet, it will call VLAN input. If it is some other special packet, it will call other functions. And in the end, it will figure out what kind of protocol it is and move it further up. Now, between the network interrupt and the actual network stack, there is a barrier that that was added in the old times. That's the difference between SPL-NAT and SPL-soft-NAT. So the interrupts want to be processed very quickly, and the rest of the network stack should run with lower priority. So what's happening was that the ether input is deciding what kind of protocol is used, and then puts the packet onto a protocol input queue and schedules a software interrupt. And afterwards, the software interrupt is scheduled and produces these NAT ISR, these interrupt, scheduled the interrupt service routines there, which are like IP interrupt or IP6 interrupt, which then will dequeue the packets and call the input functions of the network layer. So in most cases, it's IPv4 input or IP6 input. And these functions will then start reading the packet, figuring out if it is actually a valid packet. And one of the first things they will do afterwards is calling PF test to do the input firewalling. The next thing they will do is figuring out if this packet is for a local host, if it is for the machine itself, or if it has to forward it, if it is So either it's moving it upwards to the layer 4, or it's actually moving the packet to IP forward, where the route lookup will happen, and the TTL magic of decreasing the bit TTL will happen, and then the packet will be pulled again out. If the packet is for a local system, we're moving over to a so-called proto-switch structure to find actually the layer 4 protocol. So why is this proto-switch structure there? So the idea behind it is to bring some object-oriented concepts into the network stack. So every protocol registers one proto-switch structure and fills out some function pointers. And so in the end, you can do something like method calls and just say, I have this packet, just handing it off to the protocol, and you don't really have to hard code any protocols inside IP. You just have to fill out the proto-switch structure, and you add your new protocol to the network stack. So through the proto-switch structures, various input functions are called. So these can be TCP input, UDP input, or RIP input. These functions will do, again, the verification of the packet. And one of the first things it will do is finding the corresponding PCB. So the PCB, every socket has a PCB assigned to it. So PCB is the lower part of the socket. And in the PCB, every information necessary for this specific connection is stored inside it. So this means, like, for UDP, it's mostly like the port numbers and the IP addresses, but for TCP, flow control, retransmission logic, reassembly logic, and every other state information is inside this PCB. So it's quite a huge structure. And it's also so that this input function for the reliable protocol like TCP is very complex because there is a lot of stuff to do inside there. Whereas for UDP or for raw IP input, it's very simple because you just take the packet, say, okay, it's the correct packet, and then you just can queue it. You just queue it into the socket receive buffer, and then you wake up the user land. And in TCP, you have to do a lot more coding for that. Now, when user land wants to send stuff down, you're coming in with SO send. So that's the first function of the socket code that's called up. SO send will now use again the proto switch to find the protocol that needs to be called and calls the user request function of that protocol. And these functions then will just like play a little bit of a record role and just call the corresponding output functions of these of the protocol. So there are now more protocols as we see here. This is a RIP6 and a UDP6 output function, and we have a UDP and a RIP output function. The reason behind that was that UDP and RIP is very simple to implement, but there are certain differences between IP6 and IPv4. So you have different pseudo headers for the checksumming, and you have perhaps a few other options that you can enable or not. So it was easier to just copy the code over and do do it completely new than like trying to merge everything together and decide on the end. On the other hand, for TCP, which is a lot more complex because of the reassembly logic and everything, it was easier to actually just play this game of figuring out, okay, here we have IPv6, we have to use this header instead of that one here, and do these games, and then in the end decide based on the address family what output functions on the lower level we have to call up. So the really important thing is that we call the network output function more or less directly. So there is no proto switch for the network layer. Then in the network layer, we're getting packets from the layer 4 and also from the forward functions. And IP6 input is more or less doing a very simple job. It just prepends an IP header, then calls the PF test function to do an output packet filtering, and does the root lookup. And as soon as it has it did a successful root lookup, it knows where to send the packet, which is the outgoing interface. And it uses the interface output function, which is as well like a little bit of an object-oriented thing, that we have a function pointers inside the interface structure, and it just can call the IF output functions and doesn't have to know if it is now an Ethernet interface, or if it is an BBP interface, or if it is an ATM interface. You just call the output function and you're done with it. So in the link layer then itself, this interface output function is backed by multiple other output functions. So there is, again, Ether output, which is the one that probably most traffic will flow through. And then there is LO output, which is the loopback output function. There are a couple of others, like SPBP or IEEE 802.11 for the wireless stuff. And what these functions most of the time do is they're prepend the layer 2 header, and the other most important part they have to do is figuring out the link local address of the remote site we want to talk to. So we have to call argresolve or ND network discovery functions to figure out what is the MAC address of the remote site. When we have figured that out, we can actually start to send the packet onto the wire. But again, here we have this barrier between softnet and the real network interrupt priority level. So here, between here, we have to queue again. And that's actually where we do then the where alt queue is happening. So we enqueue the packet onto the interface queue, output queue, and later on we call up the interface start function. We will then dequeue the packet again, and alt queue is just changing the way this queuing happens, because it knows that it can tell you, yeah, you have enqueued something, but it's not yet ready to get out of the queue because you already sent too much traffic in this specific class. So this is where that happens. And at the same time, we have to switch from softnet to the SPLnet. The IF start function is normally provided by the driver, and the driver will do then what it does. It takes the packet off the packet queue, puts it on the DMA ring, and makes off the driver, the hardware to say, here is more memory, here is more data, put it on the wire, and inform me when it's done so that I can clean up later on. So this is how the network stack more or less works in very, it's a very short introduction. One big part of the network stack is routing. So the routing table code is probably all over the network stack. It's even in some other probably not so networking heavy directories, like it's even NFS is using routing table code, and so it's spread all over the kernel actually. It doesn't only hold the network forwarding information, but it also has the link layer addressing stored in this tree. So it is address family independent, so we have one routing table code that just matches for IP, IPv6, and even for ATalk, Apple Talk, or like was used for ISO addressing. And there is a lot of matching happening in there, and that's also where a lot of the dragons are hiding inside the network stack. This is more or less a short picture of how the routing tables more or less look like inside the kernel. So we have a address family to routing table index array that allows us to only allocate a minimum of routing table head nodes because the the address family array itself is quite large. We have something like 32 or something address family defined in the BSD kernel, but honestly, normally only 2 are used. So it does not make sense to allocate everything from every AF, a head node, when you can actually compress them. Then we have the head nodes and the trees itself. And at the lead nodes, we have the so-called RT entry, where all the information is stored on the route. So there is the next hop stored inside there. We have other stuff stored inside there. We have a pointer to the output interface stored inside there. So we know with the RT entry, you actually have everything you need to do routing. We extended the routing table code in the last couple of years with a few features. So we have added route labels. We enabled multipath routing. We have now multiple routing tables. And the last 2 things are stuff that we're working on. So we're working on making routing domains, which is something that in Cisco speak is normally referenced to as virtual routing and forwarding. And the last one, routing priorities, is something that's mostly something internally for making it easier to handle the routing needs that we have in user land. So route labels. The idea behind this is that we can tag routes with a specific label and just name a route with something. And inside the kernel, we then replace this label with an integer that we attach to the node. This is the idea behind this. It's faster to compare 2 integers than to do a string compare of 2 strings. And the trick behind this is that, like PF or the root entry itself, they're normally set once and then used 100,000th time afterwards all the time. So this makes sense. And we have for this, we have a special name to ID lookup table inside the kernel where we matching these IDs to names and also in the reverse direction, of course. These tags can be inspected by various sources. So PF can filter and tag based on route labels. In userland, we can play around now with like BGP. BGP can set route labels based on BGP path attributes that you can use in the filter language to set stuff. OSPF and RIPD can redistribute routes based on route labels. So you can specify that you want to have this and this and this route be announced to other OSPF routers. And then you can actually start playing games with BGP and OSPF together. That BGP is inserting a route with a label, and OSPF is afterwards redistributing this route because it has the same label. OSPF can even set the route labels based on the external routing tag. So OSPF can play quite a few games with route labels that are very interesting. Multipath routing. Multipath routing is more or less the idea that you have multiple routes to the same destination. I will now speed up a little bit because, yeah, I have a few problems. So the idea is that you have multiple routes inside your kernel, and we can have used the already existing routing table code because it already has a concept of having the same key inside the tree multiple times. So it was something pretty simple to do. And most of the multipath routing code was actually coming out of Penny because I think the first big idea was to use it together with IPv6. We are using a hash of source and destination port pairs to schedule the connections so that we can reduce the packet reorder problems. Packet reordering is normally very bad for TCP sessions because it will reduce the performance of TCP massive. This is more or less a picture how this works. So we have multiple entries that are all have the same key, and we're just comparing if the address and the net mask are the same, and if they're the same, we're doing multipath routing on that. And if they're not the same, then it's just a more specific route that just should normally be used. A few things you need to think about when using multipath routing is that, like, the return path may be actually going to another box. You have problems with outgoing connections that are coming from your old machine because we're doing the bind of the socket before we do the routing. So it's possible that you bind to interface A, but in the end you're setting out the packet on interface B, and this can normally be problematic if you have anti-spoof or unicast reverse forwarding checks inside the on some firewalls inside the network. One big issue is that we don't detect link loss, so you need to be really sure that your two multipath routes, for example, are always up, or if one goes down, you suddenly have like lost 50% of your traffic. You can probably play around with this with IFSAD and little shell scripting to add and remove routes as soon as the link drops. You have to enable multipath routing. We have the switch control for that. And this is more or less how you can add and remove routes. If you want to add multipath routes, you normally have to add the -npass switch to the route command so that it actually accepts the additional route. And if you delete the route, you have to specify the next hop or it will fail. Multiple routing tables, the idea is that we just not only have one path node here, but we actually have an array of them. So we have suddenly multiple routing tables that are just like all different and can have different information inside them. So the kernel now supports multiple routing tables. There is currently a compiled-in maximum of 256 tables that we have. And by default, we run on the table 0, and you can use PF to classify the packets and say, use table 1 or use table 7, and this is what all is currently inside the OpenBSD even 4.2 kernel. So we're just we just can switch to tables on the forwarding path. We don't have any link layer information inside these alternate tables, and more or less the only program that supports multiple routing tables is currently route. BGP has a few hacks in it to actually be able to say, okay, I'm now only playing with routing table number 1 or routing table number 3, but it's not able to actually talk to multiple routing tables at the same time. This is more or less how it works. The big thing is that there is now a big T flag to route, so you can do all the commands on specific tables. In this example, it's always the table 1 I was using. Then routing domains are more or less these multiple routing tables, just a little bit enhanced. So the idea here is that we're extending them by binding actually interfaces to these tables. So we start storing the link layer addresses inside these routing tables. And by doing that, we're suddenly able to have the same network configured on multiple interfaces, and they're actually not conflicting in each other. This is normally used to, like, in ISP setups to connect multiple customers with the same networks and then play VPN games inside your own network for that. One big issue was that the routing socket needs to mark all messages now with a specific table or domain ID. And because of that, we had to change all the routing socket messages. This was done in 4. This will be done in 4.3, and So we will now be able to actually start using that whole concept. One big issue is that like userland needs to filter by itself all messages they're not interested in. So they have to say, okay, I only want to know everything about table 0, and then it has to just drop every routing message that's not for table 0. One big problem is that we have to ensure that no packet can leave a domain. So whenever a response packet is generated, we need to ensure that it is actually in the same domain. It's not possible to leave a domain. Now, because it's not possible to leave a domain, you need an interface to actually connect two domains together. So you need to have like a leaf-top loopback interface that has one end of the side in one domain and the other end is in another domain, and you're just switching the IDs in this driver. Userland needs to be able to find sockets into specific domains. This is like for ping, it's necessary that you can ping like in another domain so that you can figure out if now in your domain 3 that a holes in there is actually up, and you cannot run that on the default routing table because that will not work. And there are quite a few things that are still a little bit unclear, and it is so that we are actually doing now a network hackathon where I think one of the main targets is actually to figure out what we have to do to make this actually work, and how we solve some of the interactions that are at the moment still a little bit in the open. Now, routing priorities are something completely different. The idea behind routing priorities is that currently we have a lot of userland routing daemons that start talking to the kernel and putting routes into the kernel, and they have their view in userland, and then there's the view of the kernel, and this needs to be in sync. This is normally a big problem when you have a conflict, like BGP and OSPF have the same route and both want to add it to the kernel. You may have the problem that like either it's just like the one that's first that wins, which is quite a bad situation because depending on how you boot the system, it may be OSPF or BGP. And so you actually want to have a preference that you can say OSPF wins always over BGP. Doing this synchronization in userland without some is pretty difficult because you have race conditions. All those daemons have to have a global policy that they actually follow. And one of the biggest problems is that our routing socket is lossy. So when you're sending a lot of messages down, it's possible that other routing daemons do not get all that back. So that's something you have to consider. So we need a solution. Now, there are two ways of doing it. The common way is that actually what Steerak, Wagga, Xort, and other routing projects are using is they have one userland process that talks to the kernel through the routing socket, and all other routing daemons or everything that wants to change routes actually have to talk to this daemon. Now, this adds a lot of code and also a little bit of unnecessary code because we already have all this infrastructure inside the kernel, and at the same time it adds a single point of failure because when this userland daemon will die, it will just like nothing will work anymore. You cannot change your routing table anymore, and it's just like you probably have to reboot the box. So we can do this in the kernel, and when we now thinking back, we realized, wait, we already have the possibility to store networks to the same destination inside the kernel table because we're able to do multipath routing. So we're just adding some sort of metric to a route and then sort the multipath routes as in an ascending order inside these multipath routes, and then just say, okay, we only select the ones that have the minimum metric. So we define a few metrics that say, okay, the connected routes are the most preferred ones, and then we have static routes, and we have the internal data protocols, and then we have the external protocols. And by doing this, we suddenly solve this whole problem of having multiple routing beacons in the user lane. And the kernel will just always do the right thing. So we're doing more or less just like beforehand. We just have the same address multiple times in the network stack, and they have different X-talks, and they have different priorities, and the multipath code will just like now start looking also at the priority and say, okay, this has a lower priority, so I would always take the first one. And then it would say, okay, this is actually would be multipath capable, but it has a different priority, so it's not an equal cost with multipath route. And we'll then stop using that route. This is what I said, we're going to be using multipath code. And it's now important that you define a priority that when you add or delete the route. The kernel will try to select something smart for you if you don't specify it, but especially the routing daemons should actually set something. So the basic functionality is implemented, but yeah, it's the typical routing nightmare, or actually probably the typical network stack nightmare. It is so that every time you start hacking in the network stack and you start making bigger changes, you normally end up at the beginning with a really evil crash. And then you work further on, you fix your crashes, and you think, oh, now it's working. So you're giving it to a bigger group to test it, and now suddenly somebody else's system is crashing because he has a different scenario. And then you have to do revert, and after a long time you have fixed it. The other thing is that like routing table is used all over the network stack and even in other parts of the kernel. So like I had suddenly to change code inside NFS, which is like shouldn't really should have something to do with routing, but it's needed for NFS for disk bus systems. And so you suddenly have your obscure changes that you have to do. And yeah, then we have the typical open source problem, lack of time. So you should actually have a lot of time to hack on this stuff to make it run. Now, my last few bits, this is more or less my to-do list, or stuff that people could do. I would just like title it now because I'm already over time. There is stuff like route validation, so figuring out if a route is actually valid or not based on the interface state. A large project that I would like to do is MPLS and LTP. At the same time, I would like to have multiple bits inside BGP and perhaps OSPF, so and then use BGP plus MPLS plus the routing domains together to get a real virtual routing and firewalling scenario that can actually like connect to a bigger Cisco network or actually replace one of those networks. Another project I would really like to see happening, which is actually pretty simple, is having the possibility to do routing socket filters. We have a lot of userland applications that listen to the routing socket just to figure out if the link state is changing, like DHC client. Now when you run BGP and DHC client in the same box, you suddenly figure out that DHC client is using a lot of CPU time when BGP is starting to pull a lot of routes into the kernel because it's getting all the messages and it has to read them in and say, oh no, I'm not interested in it, and removing the packet from it. So this is unnecessary. It would be nice to actually be able to build packets. A really important project is actually the cleanup of the end-to-end matrix. we need to ensure that we find a better way to use the mbuf, that we have functions that have not so evil side effects that they're mostly that they're more or less correctly used, not as we have at the moment, where a lot of functions drivers are using functions in the wrong way, probably cause later on really evil problems like crashes. And a real old project that I always have in my slides is replacing actually the routing table code that we have at the moment with something that is more like the 21st century style. So the old routing table was designed on systems where an addition or other instruction has more or less the same time, needed more or less the same time as a memory access. So it was doing a lot of memory access to figure out where to go. And this actually is a big problem on current CPUs, where actually memory access is like hundreds or even more times slower than doing like additions or other bit field operations. So it would be more, it would be a lot cleverer to invest more time figuring out which memory you have to access than to just like go and do a lot of memory access. Yeah, that was more or less my talk. Are there any questions? Yeah?
I'm pretty tempted by this multiple routing tables.
Yes.
This is the thing that I'm missing the most. That's why I have to finish from my multiple computer.
Yeah.
And where you get to just simply put a couple internet lines and just mark packets like count HTTP traffic in this one and everything else this one or something like this.
This is currently already possible, yeah. What's not possible is like you cannot have the same the same networks on your outgoing interfaces. So you cannot do some really evil tricks with it. But what you can do is you can use multiple tables and then say I want to use this table for like my HTTP traffic, and I want to use this table at this interface for all my QoS VoIP traffic, because that's a better, faster link or a low delay link. And you can do that already. Yes. Any other question? Yes?
I am very curious to know OpenBSD network stack more.
Yeah.
So what is the next action you recommend to me?
I think a good start is actually to first get like the Stevens book and at least start looking a little bit at it. It covers a lot about how the network stack is working, and it has a lot of chapters about like mbuf handling and about the socket API and everything. So you get a good overview of how the stuff works, and it also has like, it tells you in which directory you have to look at the code. And when you compare the code to what's currently in the BSDs, you see it's still very similar. So you can easily like say, okay, I have this code, I don't understand it, and then you go in Stevens and searching that function and say, oh, it's still mostly the same, and then you start reading the commentary, the comments that Stevens made about the function, and then suddenly they say, ah, that's why the code is like this. And I think that's very helpful. And the other thing is that you should actually try to find a project that you're really interested in, and don't make it too big. Like, if you have a certain problem, try to solve that, and don't. And if it is enough small, you don't have to touch every file inside network stack, and then you can slowly learn by reading code and by changing code, and you're also getting happy because you're solving your own problem It's really hard when you're working on a project that you're actually not really interested in, because then your motivation is not there.
So what is Steve's book?
It's TCP/IP Illustrated.
Oh, I know. Thank you.
That's a real fat book, and it's the #1 network. I think it's the network Bible.
I know.
It's 3 books.
I know.
And if you want to do IPv6 stuff, there is the book from Jin Mei, which is IPv6. What the name is? It's the IPv6 core protocol implementation book from Jin Mei. There he explains how the KME code was implemented and what's the reasoning behind that. So that's also a very good book.
Thanks a lot.
Yes?
You mentioned about the mbuf API libraries.
Yep.
And once I read about Linux kernel implementation about routing, that is implemented in a different way.
Mm-hmm.
So, if you have any comments about those implementation methods?
Linux has a different notation. They don't have mbufs, they have something similar. But it's working a little bit different. And I'm not really sure if their implementation is much saner than ours. The main problem with the mbufs is that, especially in the input path, where it's just like we're storing pointers that point into an mbuf chain, and then we're calling an mbuf function that may change the chain. So suddenly the pointers that we had beforehand are no longer valid afterwards. And you really have to be careful that you remember that, okay, this function will modify my chain, and so my pointer that I was using beforehand is now no longer valid, and I have to re-get the data. And if it would be good to try to minimize the mbuf API to have less side effects, or if they have side effects, that they are just more easily handleable. And I think I talked to a couple of people here, and all were like, yeah, it's mbuf API, that's just horrible. It's actually not an API. It's just functions to fiddle around with mbufs.
Thanks.
Okay, I think we should stop now so that the next talk is not too much delayed.
The next talk in here will be Sleeping Beauty, putting NetBSD laptops to sleep by Joe